Morning. Good morning. Welcome to Krishna's class. We continue with our exploration of the fundamental theorem of calculus in the context of Lebesgue integration theory. Now we have done all the preliminaries. We called it also in our last lecture, and all the results that we have already proved have been collected together and given in that lecture so that it's easily accessible. Just a recollection. Now, we also observed that the differentiability of the functions get affected once the function is too rapidly oscillating. Now, the reason is this. You just look at this one. Suppose this is the function. Graph is clear. Now you see that the derivative is the tangent to the function at some point. So it gives the slope of the tangent to the function at a given point. Now you see that the function starts oscillating. That means this peak becomes very sharp. What happens is that in the neighborhood of the point, you see that the tangent, the slope of the tangent becomes very large. Now this is one problem that you have. Therefore, eventually there is a chance that if the function is too rapidly oscillating, then the slope of the tangents at the peaks may get unbounded. Now this is roughly the reason why we feel that the function, the oscillations of the function has to be restricted. And what we have already seen is that the absolute continuity is a notion which puts a restriction on the oscillation. And therefore, we hope that absolutely continuous functions are going to give us the necessary class of functions. Okay, what is the fundamental theorem of calculus? It says the following. It says the following relationship between the function and its derivative is valid. That is, if f, let us work on rather nice functions, or even C1AB. That means functions whose derivatives are also continuous. Then we have integral a to b. Because we are not satisfied with such a heavily controlled function, and we are interested in probably relaxing this restriction C1 to the extent possible. Still, the validity of such that the validity of the fundamental theorem of calculus is still valid. Now, how far you can go? So this is the question that you are asking. You would allow the function to have some kind of oscillation, but not far too much. Okay, because you know that oscillations do spoil the slope of the tangent. It becomes unbounded. This is one of the problems that is. Now, for the purpose of this analysis, now this is the continuous version of fundamental theorem of calculus. Now we write down the discrete version of this. Assume CA extend F take the value FB on the reason will be clear why we want to do this extension. For less than or equal to 1, define the divided difference function x by f of for 0 less than h less than or equal to 1. Now this is the reason why we have extended f over the part b to b plus 1. This is what we have. This is a, b, c, d. So we have a function here and we have extended it over to this interval so that f of x plus h when h lies between 0 and 1 makes sense. Oh, this is well defined. Okay. Further, we find the average value average value function by FTDT. So that's the definition, average value. So we have two functions now, difference function and average value function. Now, you know that under favorable circumstances, as h tends to 0, this integral tends to f of x. Similarly, as h tends to 0 over here, you see that the difference functions converge, tends towards the derivative of the function at x. So we now write the discrete version of the formula. Discrete formulation of the fundamental theorem of calculus. A as integral a to b a b x for 0 so this is the discrete version of this formula. So we'll be working around on this result. Okay. Now we can in fact give a quick proof of this result. Proof of the discrete version. Now you observe that integral a to b f. This is equal to, by definition, this is 1 by h integral a to b f plus h dt. So you see that by our assumption all these are well defined. Now that's equal to dt. Now this here we introduce a change of coordinates, then you see that this is equal to 1 upon h integral a plus h to b plus h dt by a change of name. T plus h equal to s or something minus 1 by h of dt. Therefore, this is equal to 1 upon h Now look at this one. This is essentially, you have A, this is B. So it's actually the integral over A plus h to B plus h. From that you subtract the integral of f over integral A to B. Now splitting this integral and rewriting the whole thing, one observes the following. Now this may be shown to be, and that's just it. Just very simple. Now this is equal h integral a plus h to b plus integral b to b plus h s integral integral h integral a plus h b So you see that these two integrals cancel out. These two cancel out. They are left. Let's see. integral is equal to at b. So that proves the discrete version of result. And we shall be requiring this for our purpose. And now we shall write down the characterization here. Characterization. Theorem that we are so we make the statement now. Let be continuous on the closed bounded is f belongs to C assumption that we make. Then f is absolutely continuous on AB if and only if that is the characterization. But the family of divided difference functions is a class of functions is uniformly integrable so it is connected with the uniform integrability of the divided difference functions. Okay? Or in short, you say that f belongs to CAB is absolutely continuous Uh, that's a beautiful characterization that we have, which we shall need for our further investigations. Okay, so that's the statement of the theorem. Now let us just recall what is the uniform integrability. A family of measurable functions on E family F of measurable functions on E is said to be uniformly integrable. Over E provided for each there exists a delta positive such that each F plus F whenever A contained in E is measurable and measure of A is less than delta, then integral over A of R F. Okay. The point is this. Now you see, corresponding to each F given an epsilon positive, corresponding to each F, there exists a delta. And this delta in general depends on epsilon and F. What we say is that uniform integrity demands that even epsilon positive, there exists delta independent of or universally valid for all f such that for a measurable contained in U with measure of A delta integral over A mod f. This is the debate. So this is the uniform continuity, like a notion like uniform continuity. So here the delta that you have is universally available for a given epsilon for all functions in this collection f. That's what you mean by the uniform integrability. So in our problem, the collection f is the set of all this is a class of functions. Divided difference function. So you have for each f there is a divided difference function. So you have a collection of divided difference functions, and this is the script f that we are going to use, and we demand that integrability is uniform. It is uniformly integrable on the interval, uniformly integrable on the on P. Okay, so let us now start with the here. Because our E is the interval A. So we shall write down the proof of this here. So first we assume that so we are going to prove in this direction. Assume the divided difference function is uniformly integrable A right A B plus 1. So this is the assumption. What we claim is that f is absolutely continuous That's the conclusion. So we are moving in the backward direction. Now we elaborate upon this condition by the assumption for epsilon positive, delta positive, and what I mean to say is delta is independent of the individual function such that we're talking about Lebesgue machine. Delta for 0 less than x. So corresponding to epsilon by 2, we choose the delta. And there exists such a delta by our assumption of uniform integrability. This. Now let CKDK be a disjoint collection of open intervals Then for less than 1, then equal to 1 and less than or equal to n, average value function This is equal to integral now this result we have already, okay, and which implies summation of is less than or equal to sigma k equal to 1 to n. Which is equal to integral over E f where okay, and measure of is less than that. So this is the measure. Therefore, sigma k equal to 1 to n. K is less than. So this is by the uniform integrability of. Now this is true for less than or equal to 1. Since f is continuous, by letting h2 0 plus, we get now this is because of the identity that we have proved. Okay. To recall the following. See, when see this is the part I am mentioning. See, you have got the yeah. See, integral 0 to t. Now let's or 0 to this goes to f of as h tends to. That's the result that you have to see. Therefore, you get this one f dk, and here you get f ck. And this in turn implies that absolute yes on the interval, that is f is an absolutely continuous function on the interval. I think that is the one part of the proof. The next part of the proof we'll take it up in our next lecture. So we will mark this as part 1 so that next lecture will be part 2. Okay. So tomorrow most probably will record the next the converse of this theorem of the characterization. Okay, so thank you very much. So we continue with it.